If you want to find an angle from a known sine or cosine value today, you just press a button. But historically, engineers had to run this process in reverse. Instead of starting with an angle to get a logarithm, they had to start with a logarithm, translate it to a trigonometric value, and then trace that value backward to find the original angle. To do that without a computer, they relied on printed mathematical dictionaries, heavy volumes of logarithmic tables. This data table shows how finding a straightforward angle starts by removing the archaic -10 notation these old books use. Once you have a clean starting value, you scan the rows and columns until you find an exact match, leading straight to a clean baseline angle. Finding an exact match is simple. The real mathematical challenge is figuring out what happens when your number falls into the empty, unprinted spaces between the lines. When your target value doesn't exist in the table, you have to interpolate. This means identifying the two closest known values your target sits between. The total mathematical distance separating these two printed dots is known as the tabular difference. Here, the gap is exactly 14 units wide. If our required value is 6 units above the lower dot, we simply calculate 6 divided by 14. That tells us our true angle sits exactly 42.9% of the way towards the next minute. But calculating that gap requires paying close attention to which function you are using. With sine, the relationship is direct. As the angle gets larger, the sine value increases. Cosine does the exact opposite. As the angle grows, the cosine value shrinks towards 0. This inverse behavior dictates the interpolation math. If your required cosine logarithm is larger than the printed table value, you have to subtract your interpolation percentage to find a smaller angle. Finding that angle is only half the battle. Because trigonometric functions map to a circle, there is always a second, equally correct angle hiding somewhere in the rotation. We locate these hidden twins using the unit circle. The sine chart divides this circle into 4 quadrants, tracking exactly where sine, cosine, and tangent are positive or negative. If your book gives you a reference angle of 30 degrees for a positive cosine value, the chart shows that cosine is also positive in quadrant 4. You subtract 30 from 360 to reveal the second answer, 330 degrees. Now, test the process. If you have a negative tangent value and a reference angle of 45 degrees, pause the video and use the chart to find both correct angles. Tangent is negative in quadrants 2 and 4. Subtracting the 45-degree reference angle from the 180 and 360 degree marks gives us 135 degrees and 315 degrees. Older textbooks also throw in obscure functions like secant and versine. These are just algebraic costumes. Secant is simply 1 divided by cosine, and versine is 1 minus cosine. Once you strip away those costumes and convert the numbers back into a basic sine or cosine value, the unit circle will always guide you to the correct physical angles. There is one edge case where this entire manual process breaks down. When dealing with tiny angles under 3 degrees, standard straight-line interpolation fails. This graph shows why. As the angle approaches 0, the sine curve bends far too rapidly relative to the tiny angle intervals. The straight line we use for interpolation diverges from the actual curve, creating a growing error. To fix this, navigators and engineers relied on special S&T correction tables. These acted like fine rulers, allowing them to measure microscopic shifts down to the arcsecond. These fine adjustments rely on a specific mathematical reality. At an extremely small scale, the sine of an angle is practically identical to the angle itself. Bringing it all together, you first clean up the logarithm, then use the table and interpolation to find the reference point, and finally check the unit circle to map every valid angle. Whether you are paging through a dusty textbook or pressing a button on a modern calculator, working this process backward means you are manually executing an inverse function, and understanding how to invert a function is a skill you will carry straight into calculus, physics, and complex engineering.